Okay, so let's take a look at this problem very carefully. Okay, you understand that we have two different types of candies. Let's call candy, the $2 pounds is candy A and the 360 is candy B. All right, you want to make a total of 50 pounds of mixed type, meaning you're going to put candy A and candy B together in one bag, and then you're going to try to sell 50 pounds worth of mixed candy at 2/16 a pound. Do you see that scenario? Yes? Okay. So how do we start doing something like that? Well, first of all, you got to ask this, you got to look at the question and say, well, what is it asking me to do? It's trying to ask me to figure out how many pounds of each type I need to make a total of 50 pounds. And yes, in your mind, you probably just start testing now. Oh yeah, what if I have 1 pound of this type and 49 pounds of the other type? Or 2 pounds of this and 48 pounds. And then just keep on coming up with different combinations until you get to the final answer. But then again, that'll take too long to do, right? This is the reason why we want to start coming up with an actual equation for it. And let's be very specific. You read the question, it's asking how many pounds of each type. In this case, I have 2 types, so I'm going to be very clear and very specific. Let's declare X to be the number of pounds of the $2 per pound candy. Okay, notice I'm declaring very specifically of what X represent. You don't start by writing X and Y without telling me what X and Y are. Is that clear? Or A and B or C and D, whatever. In this case, I'm going to use Y for the number of pounds of the $3.16. Or is it 60 cents? $3.60 per pound candy. So X and Y represent not the cost of the candy, but what does it represent? What does X represent? The pounds of the $2 type. And the Y represent the number of pounds for the 360. It's not the cost. We just know it's the pounds of that type. Okay. And we know that when we take the type X candy and we put it together with the type Y candies, how many pounds total should we have? 50 pounds. Isn't that basically our cap right there, that it cannot go over or under? It has to be exactly 50. Therefore, does it make sense for me to write it like this? Yes or no? Let me know right now. Yes. Because if I declare, notice that this is what? 50 pounds. If this is pounds, then these 2 units have to be pounds as well, right? Because for an equation, let's get this straight. An equation doesn't mean a variable and a solution. No. An equation means the left-hand side, whatever unit on the left-hand side, it has to be the same as the right-hand side. Left equals to the right. Pounds equals to pounds. Isn't X pound? Isn't Y pounds? So pound plus pound is still pound, right? Pound plus pound is still pound. And there it is. Everything is uniform. Nothing has changed. Here's the next step. We know we need another equation. Is that true? Because we have 2 variables. Every time you have 2 variables, you need 2 equations. So here's the next equation. What else is given to you? It's given about the cost, the money, right? So that means you know that your next equation has to deal with money. First equation has to do with the weight for the candy. Then the second equation, in this case, since we have not dealt with the money yet, you know the second equation is going to have to deal with money somehow. Money means what? How much you're going to have to pay. So in this case, let's take a look at this. If X represents the number of pounds for the $2 type, how do you figure out how much you have to pay? Let's say if I want to buy 10 pounds worth of candies of X type. Yeah, multiply, right? $2 per pound, and X is the number of pounds, so how do you figure out the cost? How do you write that as an expression? 2x. Understand why I write 2x? You know where this 2 comes from. Because it's $2 per pound, right? And X is the number of pounds. And what does 2x going to give you back? The cost. Money, right? And won't that also apply to the Y type? $3.60, and notice I write 3.6, which is the same thing as 360, right? Do you understand why I write 3.6 times Y? $3.60 per pound, and Y is the number of total pounds you're going to buy. So if you can find out how much I have to pay for that, notice that you go into the supermarket, you buy 5 pounds worth of apples, they're going to take 5 pounds times the cost per pound. Is that true? And you know that's multiplication is involved. And we also know that when we add the two up together, it's going to be 50 pounds, right? Is that true? But then 50 pounds, for the 50 pounds, how much is it I'm trying to sell? At what? How much? What's the price? 216, right? So over here it's 216 times 50 pounds worth. And notice now, isn't this going to give me money back? Isn't this money? Isn't this money? Do you see the connection there? I hope that's clear. All right, so let's kind of clean it up a little bit. 216 times 50, we found it to be what? How much is it again? 108. So I'm going to go ahead and write that. 2x plus 3.6y equals to 108. And because I hate decimals so much, I don't want to see it there at all, how do I clear that decimal? Multiply by 10, because the last place value is the 10. You see it? So every time you see decimal or fraction, clear them. So because I only have one decimal here that is in the 10th place, I multiply the whole thing by 10. And that's going to become 20x plus 36y, right? Equals to, is it 1080? Okay, once I have that new equation, I'm just going to drop the old one. I don't need them anymore. Okay, so the only two that I'm going to be using right now is the x plus y equals to 50, and the 20x plus 36y equals to 1080. Okay. You forgot the approach I showed you before. You look at this thing right here and ask yourself, is this aligned perfectly? X column, Y column, equal, and a number. If they're aligned perfectly, we can use something called the elimination method, right? Elimination method means we just have to focus on one column that we want to get rid of. Which column would you like to get rid of? Which variable, by the way? Pick one. X. Okay, let's pick X. So what I'm going to do is I'm going to circle this right here and say I want to get rid of that column. But to get rid of that column, I must have the same exact coefficient, meaning number in front of the variable. Do I have them exactly the same yet? I do not have them yet. So to find the exact coefficient, you want to look at the LCM. Who knows what the LCM is? What does it stand for? Lowest common multiple. So let's take a look. This is a 1, this is 20. What is the LCM for 1 and 20? What is it? What is the LCM for 1 and 20? 20. Okay, but this is already 20, right? We don't have to care about that. How do I make that 20? Yeah, multiply by 20. Do you see that? So if I multiply everything by 20, I will get 20x, 20y, equals to, is it 50 times 20, 1,000? Yeah. You see that or no? Okay. So once again, I'm still trying to get rid of this. So how do I take 20x and 20x to get rid of it? What operation would I use to get rid of that? Subtraction. So watch what happens. Subtract, subtract, subtract. This is gone, right? What is 36y minus 20y? 16y. What is 1,080 minus 1,000? 80. So start very complex, and all of a sudden, look at that. How do I solve for y? Divide by 16. Okay. So y now, what is 80 divided by 16? 5, huh? Okay, but wait a minute, wait. If y is 5, then x has to be 45. You don't have to think much of it, right? Because it's a total of 50 pounds. If y represents 5 pounds, then x has to be 45. Based on this first equation that we defined, pounds. So how much of each type? Well, that means I'm going to have to take out 5 pounds worth of the $3.60 type and 45 pounds worth of the $2 type to make a total of 50 pounds and selling at $2.16 a pound. Okay, is that clear? Now, once again, I want you to start using this program at home to test it, and I highly encourage. I'm going to just quickly show you here, again, making sure that it works perfectly at home. What I want you to do at home is to go straight to Google and type in this. Right there. See it? Geogebra. Just hit search.
And the first thing you see is the right side, Site Geogebra. Okay? You click on that one, it will take you to here, and it's just ask you to download it. Click on download, and it will ask you to download the software. It's going to do, so click on Web Start. So this is the one that you want to download, Web Start. Okay? And then once you're done, you will have an icon that looks like this. There. If I click on that, it'll take me to this software that I can actually use. So let's just start graphing our equation to see if we get the same answer, okay? All right, let's take a look. We declare x plus y equals 2. And x is the what type? The $2 type. And the y is the $3.60. Okay, so x plus y equals to 50 pounds. First equation, and then the second one is what? 2x plus 3.6y equals to 108. There it is. So, let me go ahead and zoom out here to show you. Ooh, I'm seeing something. There it is. So let's zoom in on the intersection right there. And if you can go ahead and click on this, there's a call intersect two objects, and I just go ahead and select the intersection point, and voila, there it is. See that? Let me show you something here too. When you have two lines that intersect at exactly one point like that, we have what we call we have a consistent independent system. Well, we have exactly one solution. I notice I'm using new terms right here if you want to write it down. Consistent, independent, when you have exactly one intersection. Okay? Now, in a case where your two lines do not cross over at all, meaning the two lines are parallel, what do you think we should call that one? Yes, what do you think? Not exactly. So when we have the other case, where we have two lines that will never cross, we just call this inconsistent system. Okay? That's the other scenario. Now, can you tell me what's the other case? How many different scenarios will we have here? What's the third case then? We have one intersection, we have no intersection. What's the third case that could happen?
Undefined.
This is undefined, isn't it? No solution. What's the other case that could happen? What can happen to the two lines? Crossing, not crossing, and then what can happen? What's going to happen to the lines? Can you visualize that to see what can happen to your lines? Yes. But that's still crossing over at one point. That's still consistent independent. Yes, yeah.
More than one is consistent. More than one.
How? How could that happen?
It's just one line.
Ah, so you mean in one line and there's another line right on top of it, right? Is that true? So the third case is when you have a line going like this, and then you also have another line actually right on top of it, crossing at every single point. Now in that case, what do you think we should call that one? Let's see if you can actually come up with a name. This one right here is called consistent independent. This one is inconsistent. What do you think I should call that one? Yes?
Consistent independent.
Very good. It's called consistent. Consistent means yes, there's a solution. There are or is. And because this thing depends on the other one, we call it consistent dependent. And please make sure you know these three terms as well. Just in case I give you a graph and ask you what type is it, you should be able to describe what's going on. For the most part though, for our case, it's almost always going to be consistent independent, meaning there will always be one solution. But then, sometimes you have no solution, and at least you can just say, yeah, this system right here is inconsistent. You want to be able to use the right word choice to describe it. Okay? And another case where you have one line just right on top of the other line, we'll just call that consistent dependent system. Okay? And there it is. That's what I want you to get from this lesson as well.